So completely unrelated to volume and all the surface rotations, or the region rotations. It will be tangentially related because what we're going to do after arc length is surface area, where you're basically going to take an arc length and rotate it into a surface. And then we're going to go find surface area. It's going to be just like arc length. So first doing arc length, let's think about a curve from A to B. Here's our curve. So arc length is very much not area under a curve. It is actual distance you would travel if you went from first point to last point along this road right here. So how do we do that? What we did before was basically break it up into smaller pieces. So what we're going to do is break this curve up into small pieces. And we're going to pretend that each piece is a line segment. So breaking this into pieces, we'll just break it into a very few pieces at the beginning. So let's just break it into 3 pieces, keep it simple. When we broke, let's see, the area under a curve into rectangles, your rectangles could be sometimes a little bigger, sometimes a little smaller. Your estimate might be an overestimate, underestimate. There is one thing I can say about the estimation using line segments and a curve. It's always going to be a little bit bigger or a little bit smaller than the actual distance. It's always going to be a little smaller. But if I keep going with more and more and more segments, it's going to get closer and closer and closer. That difference is going to get very small. If I did probably 10 line segments, it would be pretty close. I think with this resolution, it would probably look almost the exact same. If I did 100 line segments, that would probably be good enough for building a bridge or something like that. So we're just going to say there's 3 at the beginning, keep things easy. And how do I figure out I need to get the length of each of these segments right here. So let's just go and think about this middle segment. How do I get the length of the middle segment? So I need some x values. We'll call this x. We'll go xk. And we'll call the next one xk plus 1. And of course our curve needs to be represented by a function. So our curve is y equals f of x. So let's just sort of zoom in on this line segment right there. So if I label these points, their x-coordinates are definitely the xk and xk plus 1. How do I get the y-coordinates? So I have my function y equals f of x. So I could write yk plus 1, but what I'm going to write instead is f of xk plus 1. Any questions on that idea? Pretty much just stuff we've done before. Once I know xy coordinates, how do I get the length of that line segment? This is probably the first question I asked you in pre-calculus 1, if you were with me from the beginning.
Square root of...
So I need the distance formula between 2 points. How does that work? Just construct a triangle, a right triangle. We're going to call this side delta x, k for the change. How much did x change from k to k plus 1? And call this side delta y k. So delta just means the change in y's, and delta xk the change in x's. So the length of the kth segment, we'll call it LK, is square root delta xk squared plus delta yk squared. So that should make sense from the Pythagorean theorem. And now we're just going to write in what are these actual values. And let's go with so for yk, we're going to use calculus here. So let's do a little work first. So we're going to use the slope at basically at xk. So we're going to look at the slope at xk, and if I use the letter m for that, so I could write it as delta yk over delta xk, and one way to write that, so all of these are going to be approximations. So it looks like right here, if I zoom way in and look at the actual slope of this curve, is not really that close to the slope of the line segment. However, if I chose super small line segments, then you can see that it's going to get pretty close. All right, so I just want to warn you, this is going to look misleading because I only broke it up into 3 line segments. So this only gets accurate if you start breaking into a lot of line segments. So, and if I went way more than that, if it was super small, it gets really close. So the idea is these are approximations unless you have a lot of, if you break into a lot of pieces, then things get really accurate. So it's going to look super misleading on 3 line segments here. But if you think of just 10 line segments or so, it starts to get a lot more accurate. So our slope at xk, right here, if I use calculus, is going to be f prime of xk. So that's going to be the slope of the curve at that x value. So this gets into just calculus 1 concepts. What is slope? And is basically derivative evaluated at the point. So that gives me the slope of that tangent line, which is pretty close to delta yk over delta xk. All right, so using this, what we just did right here, I'm going to multiply by delta xk. So we get delta yk equals f prime of xk times delta xk. So our yk, delta yk, how much y changes, is going to be the slope multiplied by the change in x. So that's how we're going to get our delta yk. And now just filling that in. Delta xk squared plus delta yk, I'm going to swap that out for f prime xk times delta xk, whole thing squared. So distributing that square to the product right here, we get delta xk squared plus f prime xk squared delta xk squared. What algebra can I do to this? Factor out delta xk squared. And the good news is it can go all the way outside as regular delta xk. So we're going to do that all at the same time. We're going to get 1 plus f prime xk squared, and then outside the square root, delta xk. So that is the formula we're going to use for LK. So that is the length of the kth segment. How do I get the length of the entire thing? I go and add up every single line segment. So total length equals sum of these segments. So we're going to write summation LK, k equals 0, and there'll be n pieces. And write down the formula for this. Summation square root 1 plus f prime x k squared and delta xk, k equals 0 to n. This is approximation. So better be careful about writing that approximation not actually equal. Ooh. So this is approximately the sum of the k line segments. How do we make this equal? We get more and more accurate the bigger and bigger n is. So all I have to do is break it into infinitely small pieces. Calculus is easy to do. Take a limit. So the actual length is equal to lim, which variable do I send to infinity? So I want n pieces, or an infinite number of pieces. So I want limit n to infinity. Summation k equals 0 to n, square root 1 plus f prime xk squared delta xk. And this turns into integral. All your xk's turn into x's, and your delta xk is dx. So this is 1 plus f prime x squared dx. And of course you're going from A to B. This formula is arc length, the one that should go in your formula page. So when you take the limit, that's goes back to calculus 1, where the limit of a summation is going to be an integral, where certain things change around. So your whatever your xk was is just x now, and your change in x is now dx. So underline that's the delta x part is the dx, and the xk part right there is just x.
Does it have to be a limit to infinity for that?
Yes, so the limit is what makes these equal. So the idea is if you get smaller and smaller and smaller line segments, you'll get closer and closer and closer to this right here, this integral. And if you actually send it to infinity, you get equality.
So an integral is kind of like the limit to the sum.
Yeah. So this is sort of glossed over depending on who taught your calculus class. Maybe if I feel like it, I'll make a video proving why this actually works. It's in your calculus textbook. It should be, I want to say in chapter 5, right where it's right after Riemann sums. So somewhere middle of chapter 5 before they do any like substitution and all that good stuff. It uses the mean value theorem and the fundamental theorem of calculus to do this. And they do it with approximations. All right, so this is if you had a function of x. What if you have a function of y? How would that change? Well, pretty much you just look at a curve that would need to be a function of y. So if you had a function of y, you'd be looking at along the y-axis some small big value. Now if I look at this, that doesn't look like a function. It's not a function of x. If it's a function of y, what that means is for each y value, there's one x value. So for any given y value, there needs to be one x value. So a function of y would actually pass the horizontal line test. So if I had a function of y, I would pass the horizontal line test. So this x equals, I'll use g. So this is the function x equals g of y. So input is y, output is x. So this is your situation. Your arc length is going to equal integral a to b. Everything's the same, except instead of f prime of x, our function is g, and our derivative will be g prime of y. Still have to square it, and we're going to have a dy. So basically our x and y are trading places. And I just named the function g instead of f. So that's pretty much all there is to it for arc length. So let's do some examples. And just to warn you, a lot of these lead to a trig substitution. Square root 1 plus something squared. A lot of those are trig substitutions. If it's plus, what is that sub? Tangent squared plus 1 secant squared. So that'll be a tangent sub right there. So a lot of these are going to lead to tangent substitutions. Unless I pick a really nice curve, in which case it may turn out to have a really nice derivative that squares into something that's not so bad. So we're going to length of the curve, y equals 4 square root 2 over 3 x to the 3 halves minus 1 on the interval 0, 1. So first of all, do I have a function of x or a function of y? Function of x. Y is by itself, so it figured any x value. Well, I have to be a little careful, but for an x value, I can figure out what is the y right here, just the way it's written. So I have a function of y. Oh, function of x. All right, so we have function of x. We are in the first situation here. So all I need to do is take derivative of f, square the derivative, and then plug it in. There's really nothing else going on. And these are x values right here. This is the x interval 0 to 1, not a y interval 0 to 1. So get f prime of x, which should be sort of nice, and then set up your arc length integral. There's really not very much going on in this problem. You can definitely set it up and find the antiderivative. So I'll give you 2 minutes to do that. Not sure where to start? Derivative is where to start. Find derivative. setup questions. So 2 squared is 4, square root of 2 squared is 2. We'll put them together to get 8. And square root of x squared is x. Do I need a trig sub? It is a square root. However, the second term is not x squared, so I don't actually need a trig sub on this one. How do I solve this? Algebra won't save you. There's really no algebra to do here. U sub. It's basically u is 1 plus 8x, so du is 8 dx. So it's a pretty straightforward u sub. So dx is 1/8 du. So at this point, I'm going to do less and less calculus in calculus 2. I'm going to do setups, but not actually solving integrals. So this should be a pretty straightforward integral to solve right here. So I'm not going to. It's going to lead to some fractions, and you can carefully take the antiderivative and figure out what you get. So questions before we move on to the next example. Sure don't. Nope. Alright, how do you know if you got the right value? Take the, well, the derivative will make sure you have the right antiderivative, but that won't make sure that you plug in the right values at the end. That's a good intermediate check right there. Ask Wolfram, what's the antiderivative? They may give it in a slightly different form, but you've probably experienced that. You've asked Wolfram for antiderivatives. I believe you can type in the full integral with the endpoints into Wolfram. I'm pretty sure. And if you Google how to use Wolfram, you could probably ask Wolfram how to use Wolfram as well. That seems a little recursive, but I'm sure there's plenty of instructions you can find online how to do integrals. These are called definite integrals with endpoints. So I'm sure that Wolfram can do this. Yes, I'm getting an enthusiastic nod. So Wolfram will be able to tell you the answer. So I think, in my opinion, anything you can just ask Wolfram for is a little bit silly for me to write down an answer. All right, next example. Hopefully we didn't screw up the writing down, but you all watched me do this, so I think we can be pretty sure that I didn't mess up the derivative. You do need to pay attention to make sure I do the right work on here. But yeah, I basically know partial work in my notes here. It's not very exciting if you know the answer, in my opinion. And the other problem is if you have the answers and you don't get to the right thing, that means you're wrong and you have to go backwards, and that's not fun either. So the good news is right now, as long as we have it set up right, we can, at least I can just walk away right there, and then it's up to you to get to the actual solution. But it's pretty much just arithmetic after you do your U sub. Alright, x cubed over 12 plus 1 over x from, now we're going to go points here, from 1 comma 13 twelfths to 4 comma 67 twelfths. Alright, if we leave it the way it's written, is x a function of y or is y a function of x? Yeah, if I gave you an x value, you could tell me the y value. If I gave you a y value, it would probably take you a few minutes to tell me what x value, or values that it came from. That'd be a much harder algebra problem. So we're going to write y equals f of x, which is x cubed over 12. Let's prep this for calculus, so x to the negative first power, not 1 over x. We're about to take a derivative, so use that notation. All right, find f prime, and then go ahead and plug that into the arc length. I'm going to give you a hint. We're going to need to square f prime, obviously. So go ahead and square it out separately, FOIL it out, and then go and plug in the f prime squared. So do that algebra separately, so you don't have to keep rewriting integral, integral, integral 5 times in a row. So simplify your f prime squared first. So calculus is probably the easiest part of this problem. Derivative wasn't so bad. Any questions on my foiling? Or all I did inside the integral was basically 1 minus a half is positive 1/2. Does this look like an integral we've seen before? No, sure doesn't. Maybe we could handle x to the 4th over 16 plus a half, but that plus 1 over x to the 4th, not so much. That's going to look a little crazy. So I don't think any of our calculus tools are going to work. So what we did up here, this f prime squared, let's think about that. That was basically a minus b squared, which is a squared minus 2ab plus b squared. That's a fast trip down memory lane. Algebra 1, Algebra 2, somewhere in between those two classes. What changed from this f prime squared down to what we got right here? Not very much changed. So that middle term became positive. So what if I write a squared plus 2ab plus b squared? You have the skills to factor this. Come on, algebra 1 question. A plus b squared. Right? Not necessarily easy to see, but I think once you see what it is, it should be pretty obvious why that works out. So it's a plus b squared. All right, so now that you know that, go ahead and factor this right here. So use that knowledge to factor this. You only need about 3% of your brain. Don't need the full 10%. So what's the only thing that changes? Basically that minus sign turns to plus. That's all the change right there. That minus sign up there turned to plus. So it's going to be x squared over 4 plus 1 over x squared. Once we're done with that not obvious algebra step, how can we, what's the next step? Square root of the square are going to go away. I don't have to worry about negatives, and why is that? It is a length, but in this particular, are there any x values that can give me negatives? They're both squared, so normally I don't have to worry about negatives, which in this case we're going from 1 to 4, so even if they were cubed, I wouldn't have to worry with our x values because they're always going to be positive anyways. This is integral 1 to 4, x squared, I'll write it as 1/4 x squared plus x to the negative 2 dx. You only need one rule to integrate. You need the anti-power rule. Add 1 to the power, divide by the power. So this is pretty straightforward antiderivative at this point. Not necessarily easy to get to that form. We did some tricky algebra. Trip down memory lane there. A minus b squared, a plus b squared. Not to be confused with conjugates, by the way. Those are not conjugates. Okay, next example. And so I'm going to write dot, dot, dot. Again, Wolfram will tell you the right answer of this right here. You'll just have to be careful with fractions, which I don't particularly like. So we can see at this point, y is a function of x. You plug in x value, you figure out what y is. All right, step 1, how do we get arc length? Derivative. So take derivative, so this is our f of x right here. So go f prime x. So we had a power rule and a chain rule happening. So make sure you get both of those constants. Multiply by the 2/3, and then you get a 1/2 from the chain rule right there. We have a slight problem that we didn't have before. What would happen if I plugged in 0 here for x? Undefined. People say that the universe explodes when you divide by 0. It's not true at all. Not in Calc 2 at least. Use L'Hopital's rule. Or decide if it's infinity or negative infinity. Alright, so because we would be dividing by 0, we have a problem here. So you could put this into an integral, but at the very end you're going to get an undefined. You might be able to use a L'Hopital's rule, dropping a limit into your integral and turning it into an improper integral, but I haven't really shown you that yet. So one way to avoid this, and you'll see this pretty soon, so I'm going to go with the blue pen right now. I haven't actually worked it out like this, but I think you probably could, instead of going from 0 to 2, you can go from a to 2. And take lim a approaches 0 from the right side, but we haven't really done that yet, so I'm not going to go that route. I believe your last step, once you evaluated your antiderivative, would probably be a L'Hopital's rule at the very end. So I'm going to say you probably could do it this way, but I'm not going to right now, because we haven't done improper yet. So this will be a cloud for the future. So you could accomplish it this way, and you would do the integral first. At the very end, you take a limit. So I'm not going to solve it this way. What I'm going to do instead is change from, instead of being a function of x, we're going to rewrite this as a function of y. So I'm going to solve for x. So we're going to basically force it to be a function of y instead. So this is called improper integral. So improper doesn't mean bad or false, it just means you got to be careful. You got to do your integral first and then apply the limit at the end. So we will be doing this pretty soon, but not right now. So we're going to instead write x as, and I don't want to use f, but I'll use, I think it would g, x as a function of y. So I just need to solve for x. All right, algebra question. How do I solve for x? What's the first thing I deal with? Power. So I have to 2/3 power, so I do 3/2 power. Is how you undo it. Don't do a negative 2/3 power. That would be improper in a different sense. That would be, so we need 3/2 power. And multiply by 2. So we got x equals 2y to the 3/2 power. And this will be our f of y. No, g of y. So any algebra questions on that? So if you want to, in the notation I did, I just took both sides to the 3/2 power. And so if you multiply power, power is product. So that's why you don't want negative 2/3. You'd be multiplying those two together, and you'd have negative 4/9. That would be a really ugly power. So you want to go with the reciprocal power right there. So algebraically we're okay. Let's go ahead and finish this off. We got g of y. What do we do next? G prime of y. So do that. And it should be pretty nice. I think it should be extremely nice, actually. Oh, that's amazing. Makes you very happy about what we're about to do. It's going to be a very easy interval. We're about to be squaring this. So it's going to be just x. So make sure you go with the dy version. So square root 1 plus g prime y squared dy on a to b, and root 1 plus, I'm going to go ahead and square g prime over here. Squared is 9y. So I did something wrong. Can you figure out what it is? Yep. 0 to 2 was x values I gave you. What type of values do I need? I need two numbers, but what do they relate to? I need y's. So I need, when x was 0, what y value would that be? When x is 2, what y value would that be? So I do not need 2 and 0. So I need to find y value endpoints. So we had x equals 0, x equals 2. I need y's. So we're going to take, let's see, how are x and y related? We're actually going to use the original y equals x over 2 to the 2/3 because I have x and I want to get y values. So we're going to plug into the original one we got right there. So I need y's. Y equals, it's going to be 0 over 2 to the 2/3 power, which is 0. What's 0 to what number is what we call, 0 to 0, right? I don't know. It's on your cheat sheet, so nobody remembers it. But it's not 0 to the 2/3 power. That's 0. I think it's 0 to 0. Alright. There we go. So that's the one you should worry about, but my point is you don't need to worry about it right here. Alright. Y equals 2 over 2. Oh, that's great. To the 2/3 power. And we got 1 to the 2/3, which is 1. And what's the 1 that we have to worry about? 1 to the infinity? That's the one we got to worry about. Alright. So we got 0 to 1. So this problem was designed to be a dy problem, not dx problem. Oh, it's time to go.